Hi there, Mr. Sutton here with the AB Calculus 613 homework answers on volume with solids of revolution. For this no calculator question, we want to rotate the region enclosed by the x-axis, the line x equals 3, and the square root function around the x-axis here. So let's find the volume of this thing. So visually, you're not allowed to use a calculator on this one, but you could very quickly draw the square root function. Here's a picture of what we're dealing with. You have your square root, you have this vertical line, and you have this region in here that we want to rotate around the x-axis. So since we are dealing with a region that's flush against the axis of revolution, there's no spaces between our area and our axis, we can use discs for this one. So then circles are going to be our cross-section area. We're just going to go with pi r squared. And in terms of x, how far is my radius from the axis of revolution? Well, the distance between my outer region of my area here and the axis is just going to be the square root. So I can just write this as pi times square root of x squared, which is just pi times x. So this is my area function that I now have to take the integral of. And what are my limits of integration going to be? Well, we're going from 0 to 3. So pi x dx will be our integrand here. And taking my antiderivative, this is going to be, let's see, pi over 2 times x squared, evaluated from 0 to 3. So we have a 3 plugged in. We have a pi over 2 that I'm going to actually take out, and then I'll plug things in inside here. So we have 3 squared minus 0 squared. So this is pi over 2 times 9, which is 9 pi over 2. And then we also have this 0 here that we don't really care about because you're just multiplying pi over 2 times 0. So 9 over 2 pi then ends up being our answer, choice C.
For this calculator-based problem, we're letting R be the region bounded by the graphs of e to the x, e to the third, which is just a horizontal line, although it looks kind of fancy, and x equals 0, that's just the y-axis. We want to know which gives the volume of the solid formed by revolving this region around the line y equals -1. So although there isn't like a decimally answer that suggests you can just plug things into your calculator and be done with the problem, we can use the calculator to get a visual of this. So let me go to Desmos and put all this stuff in here. So we've got the function y equals e to the x, and we've also got y equals e to the third, which is a horizontal line. You can't really see it because it's too high up, but we'll adjust our window in a moment. We've got x equals 0, which I don't really need to write in there, but we'll put it in there anyway. And then we have the line y equals -1, and since that's an axis of revolution, I'm just going to make that look kind of dashed. So y equals -1, and let me go to my gear and change my settings for that line to be a dashed line, just so I don't mix it up with the boundaries of the bounded region. So let me adjust my window a little bit so I can see what's going on. For the y values, let's just move this up here. Let me make my y values go high enough to see that horizontal line, so we'll make this 28. And there's the bounded region that we're revolving around the line y equals -1 here. So one thing we're going to need to figure out for this integral that we're going to take eventually is our limits of integration. So we're going from left to right. If you look at the answer choices, these are all dx sort of integrals. So this is going to be a left-right sort of integration. So we start here at 0. The line x equals 0 gives us that. But we need to figure out where e to the x and e to the third intersect. And you actually don't really need a graphing calculator to do this. Where does e to the x equal e to the 3? Well, you need x to be 3 for them to equal. But if you weren't sure, you could click on one of these, click on the dot, and see that yes, we do intersect at x equals 3. All right, so there was my graph. We said that these two things intersected at 3, so those are my limits of integration. If you look at the answer choices, they all have you going from 0 to 3, so no big surprise there. Now we need to figure out the stuff inside. And for this, we're going to need a formula for the area of my revolutions of my solid here. So for the area, because there's this big open space between the axis of revolution and the bounded area, we're going to need washers rather than disks. So I'm going to need to use my washer formula. A of x equals pi times big R squared minus little r squared. For big R squared, that's the distance between the further away part of the bounded region and the axis of revolution. The further away part of the region is this horizontal line, e to the third. So e to the third minus whatever this y value is, so minus -1, which means we really have e to the third plus 1 for that first radius there. So we're going to plug that into this formula and we'll square that. Now for my smaller radius, that's the distance from the inner part of the bounded region to this line. So that's going to be the e to the x function minus -1, or e to the x plus 1. So this is everything that I need to plug in to my integral. I'm going to be going from 0 to 3. And because I have this pi being multiplied by all this stuff, I can take that outside the integral and just leave the rest of this stuff inside, like so. Does that match any of my answer choices? Let me look at the one that has the most stuff in it, choice E. We've got the pi, the 0 to 3, we've got big R, we've got small r. It looks like E is our match.
For this problem, we want to find the volume when we rotate the region between secant of x, the y-axis, the x-axis, and this other vertical line around the x-axis. So just trying to visualize this, and you have to because this is a no calculator question. We have our secant function, which in parts kind of looks like a smiley face that's elevated above the x-axis. And we also have the x-axis itself as kind of the bottom of this function. So since the x-axis is one of the bounding areas and you're rotating around the x-axis, visually there's no space between your area and your axis of revolution. So for this one, we're going to go ahead with disks rather than washers. Our cross sections are going to be circles, and we can use pi r squared as kind of our area of our cross sections here. So the radius is just going to be the distance from your axis of revolution, the x-axis, to the top of your function. That's going to be this secant right here. So we can write then pi times secant squared of x for this area function. Now, there's no calculator allowed, so you actually have to integrate by hand. We're going to have the integral from 0 to pi over 3 of this stuff, pi times secant squared of x dx. And doing this one by hand, antiderivative of secant squared of x is just tan of x, and we also have a pi that's going along for the ride. So this is what we have to evaluate now from 0 to pi over 3. So to make this a little bit easier on myself, I'm going to yank this pi out of here. And inside of parentheses now, I've got the tan of pi over 3 minus the tan of 0. Well, what is the tan of pi over 3? I don't remember off the top of my head. This is the tan of 60 degrees. So I'm just going to kind of do some scratch work over here. This is really sine of 60 over cosine of 60. Sine of 60 is root 3 over 2. Cosine of 60 is 1/2. Dividing these halves cancel out, so you really just have radical 3. So then this is going to be pi times radical 3 minus, what's the tan of 0? That's the slope at 0 degrees, or 0 radians. So that's just 0. So this ends up being then just pi times radical 3, which is going to give us answer choice C.
For this calculator-based free response problem, we have R and S as the regions in the first quadrant shown in this figure up here. R is bounded by the x-axis and the graphs of 2 minus x cubed and tan of x, and the region S is bounded by the y-axis and those two graphs. So first part of the problem, they want us to find the area of region R. So in order to make less writing for myself later on, I'm just going to rename these functions and actually give them names so I can quickly refer to them. So I'm going to call this 2 minus x cubed one f of x, and I'll define that here. And I'll also call g of x this tan of x function. And I'll label these on the graph as well, just so we can quickly look at them and know what we're talking about. Now, to find the area of R, This is a little bit tricky because if I'm thinking about kind of distance strips and the distance between an upper function and a lower function, that's all well and good, except that we're changing functions at this spot right here. It changes from being the g function to the f function. So there's a couple ways I could deal with this problem. One would be to rewrite all of these in terms of left-right sort of functions instead of up-down functions, and then I could do some integration with respect to the y-axis. But if you haven't gotten there yet, or just don't feel like doing those conversions, another way to do this would be to just do two integrals and switch your functions between the two integrals. So in order to do any of this, though, let me figure out what this intersection spot is here. And I also need to know where the f function is crossing the x-axis. So I need a couple x values. So let's do f and g first, where those are intersecting. So where do those cross? At this point, it's time to go to my graphing calculator and actually enter these in here. And hopefully I get something that looks like the figure they handed me here. So going to Desmos, f of x, again, is going to be 2 minus x cubed. And I'm calling g of x tan of x. And let's zoom in a little bit here because, you know, this is a small piece of all this craziness. So if we zoom in, this is what we're looking at in that figure here. All right, so where do these functions cross? If I just click on one of them to get my little gray dots, here is a gray dot, and that is the x value 0.902. And I'm going to just copy that, and I'll actually call that P. You can call it whatever you want, but I want to be able to quickly grab that value again whenever I need it. So what I've done so far, I've got P equals 0.902 and some change. And I'll write that down here officially so I can use it in my work as well. Now, I also want to know where f of x, f of x equals 0. So where are we crossing the x-axis? What's this x value? Going back to my graph, let me click on f of x, and let me click on the gray dot right here, and that is the x value, 1.2599 and some other change. Let me just copy all of that, and I'm going to call that q, so I can get that value as well. Now I don't have to rewrite or refine these every single time I need those points. So I'm going to call this again q, and that's about 1.2599. All right, so I need an integral to get this r area. To get the area between 0 and, let's see, this first x value p, so integral from 0 to p, I'm going to need the top function minus the x-axis here. So that's going to be g of x minus 0, which I can just write as g of x dx. Next, I'll need an integral from p to q, and that's going to be using the f function instead, so f of x dx. And this is what I'm actually plugging into Desmos now. So let me go down here. We've got integral int, and let me just go down so I can see all that. We've got 0 to p, glad I named those, and g of x dx. So that's part of the area, but we have to add to that another integral from p to q of f of x dx. And the final area on that region is about 0.729. And there were no units given in this problem, so we don't have to give them any units. For part B of this problem, they want the area of S. So this one's actually going to be a little bit easier to figure out because we've already come up with all the information we needed. For our limits of integration, we've got the y-axis, so 0 for the x value, and the other x value is going to be this p point that we already found in part A. So we've got the integral from 0 to p. And I now need top function minus bottom function for the s region. That's going to be this f function up here minus the g function. So just f minus g of x inside that parentheses and dx. And then just go straight to the calculator to do that. So let me move this so I can see what I have here. Integral 0 to p, and I'll open a parentheses, f of x minus g of x, close the parentheses, dx, and that area is about 1.161 if I round that off. For part C, they want the volume of the solid generated when S is revolved around the x-axis. Okay, well, I just need to find the area of the things that I'm generating with this S here and integrate that over the interval from 0 to p. So I'm going to have the same limits of integration as when I was finding the area of S, only now I'm doing a volume version of this. So I need to figure out if I'm using disks or washers. Since the region S is being revolved around the x-axis, that means that there is a gap between parts of S and the axis of revolution. It's all this R region here. So that means I'm going to need washers, donuts, instead of disks. So my area formula then, I'm going to go with A of x equals pi times big R squared minus little r squared. That's my washer formula. So for the big radius, I'm going to have the further away part of this function minus the x-axis. So that's going to be the f function out there. And for the small radius, that's going to be this inner g function that's closer to the axis of revolution. So these distances here. And this is my area function now, a of x, that I can just integrate. So I've got the integral from 0 to p of a of x dx, and that just goes straight in the calculator now. Let me start by writing out my a of x function. That's going to be pi times, and in here we've got parentheses f of x, close parentheses, square that, minus parentheses g of x, close the parentheses, square it. So I've got my a of x defined, and let me just make one more parentheses there. Now I need to do the integral from 0 to p of just a of x dx, and that's about 8.332.
On this no calculator free response, they're telling us R is a region bounded by the x-axis, the square root of x, and the line x equals 4. So although this is a no calculator question, you could pretty quickly graph these out. Here's a rough sketch of what all this looks like. So here's this R region. So for the first part of this problem, they want us to find the area of the region R. Since the only functions involved are the square root function and kind of unofficially the line y equals 0, we just need to take an integral from 0 to 4 of top minus bottom, which is just going to be the square root of x. And I'll write that as x to the 1/2. No calculator, so we have to integrate this by hand. So antiderivative, this bumps up to a 3/2 for the exponent, multiplying by the reciprocal of that, 2/3 x to the 3/2, evaluated from 0 to 4. So plugging in 4 and 0, this is going to be 2/3 times, let's see, this is the square root of 4 cubed, minus 2/3 times the square root of 0 cubed. And we probably could have just factored out this 2/3, but whatever, we're here now. This second term is gone, and we could actually just leave it like this because it's all constants, but if you want to simplify it, this is 2 cubed, which is 8, times this 2 in the numerator gives me 16 over 3. For this problem, they're telling us they want us to find the value of h such that the vertical line, x equals h, which is presumably somewhere in here, divides our region into two regions of equal area. All right, so the way I'm going to set this up, I know from the last part of this problem that the total area here was 16/3. So there's some h that when I take the integral from 0 to h of this function, it's going to give me half of 16/3, which is 8/3. So I'm just going to use this already anti-differentiated evaluation box from part A. I'm going to say that this 2/3 times square root of x cubed from 0 to h has to equal 8/3. And now I'm just going to solve this for h. So plugging in h and 0, we've got 2/3 square root of h cubed. And I'm going to do all this now inside a parentheses here so I don't have to mess around with this 2/3. And now I'm going to subtract 0 square root to the third power. And that still equals 8/3. And at this point, I can get rid of this 0. I can write this if I want as h to the, this will be, let's see, 3/2 On the outside here, I could call this 2/3. I could say 2/3 h to the 3/2 equals 8/3, but I don't like those denominators. I'm just going to multiply everything by 3. So now I just have 2 h to the 3/2 equals just 8. I just multiplied both sides of this equation by 3. Now to solve, I just divide by 2, and I'm going to raise both sides to the 2/3 power, the reciprocal power. So I have h equals 4 to the 2/3. This is the cube root of 4 squared, but I mean it's a constant, so I don't really need to bother going any further than this. I'm done with this problem part. For this problem, I want to find the volume of the solid generated when r is revolved around the x-axis. Since this whole area, region here, is flush against the axis, there's no spaces in between my area and my axis of revolution, I can use disks on this one. So my cross-section area is just going to be pi r squared. And the radius is just the distance between my axis and my function here. So that's just going to be the square root of x that I'm squaring and multiplying by pi. This is going to be pi times just x. And now I'm just going to take the integral from 0 to 4 of pi x dx. I have to do this by hand, though. So this is going to be pi over 2 times x squared, evaluated from 0 to 4. And I'm going to just take this pi over 2 outside the evaluation box. So this is pi over 2, and in parentheses, I've got 4 squared minus 0 squared. So this is really just pi over 2 times 16, which is going to be 8 pi. For this last part, they're telling us we have a vertical line x equals k that divides r into two regions, such that when we revolve them around the x-axis, we get two solids of equal volume. Find the value of k. So this one works a lot like part B, where you had to find an h that gave you half the area. So looking back on the last part here, the volume of all of this stuff revolved around the x-axis was 8 pi. So I need to find a k value that when I take the integral from 0 to k, I get a volume of half of that, a volume of 4 pi. So I'm going to just start with what I already got when I took the antiderivative here, this pi over 2 x squared stuff. And that is now going to be going from 0 to k. And now I want this stuff to equal 4 pi, half of the 8 pi that I got for the whole thing. So just plugging 0 and k into this, I've got pi over 2 times k squared minus 0 squared equals 4 pi. And at this point, I'm just going to divide both sides by pi. So I've got 1/2 k squared equals just 4. If I multiply by 2, I've got 8. Square root both sides, I get the square root of 8. And since we're over here in the first quadrant, I don't have to worry about k being negative. So just positive root 8 is what we're going with.